All right, so Lagrange multipliers is section 11.8, and just like section 11.7, 11.7 you learned about the second derivatives test for determining where maxima and minimum are for functions. So, maximizing and minimizing a function of multiple variables is very important. It is an extremely important topic in mathematics. I mean, it's very important. Economics, like now what we're going to do in section 11.8 is maximize functions, try to find the maxima. We're going to try to maximize or minimize functions, okay, but subject to a constraint. Subject to a constraint. So they mention here, and I think it's worth highlighting this. It's easier to explain the geometric basis of Lagrange method for functions of 2 variables, although for functions of 3 variables it also holds. So what they have here in figure 1 is they have, maybe I can bring it down a little bit here. Let's make sure you can see it well. No. Okay, so you have a function f of x of y, and they're drawing level curves to that function. Okay, so you have a function, a surface in 3-dimensional space given by the formula f of x, y, and they look at the contour, they draw the contour plot with those red level curves. And so remember, the level curves are when you set the function equal to values. Well, if you have a constraint function, g of x, y, that equals k, you can see in figure 11, a constraint function also can be graphed as a level curve. I mean, function f of x, y equaling a number is a level curve, and a function g of x, y equaling a number also gives another level curve. So what we want to do is, I know what we want to do here, but maybe I need to move this up a little bit. So in the reading here, hold on, I got to bring it up a little bit more. Okay, so we seek extreme values of the function when a point is restricted to lie on a level curve. In other words, we want to find extreme values of a function, and I might just bring it up a little higher. I think we got to go right from the beginning here. We want to find extreme values of a function subject to a constraint. The constraint is of the form g of x, y equals k. In other words, we seek extreme values of the function when the point is restricted. The xy coordinate is restricted to lie on the level curve, g of x, y equals k. So in figure 1, it shows that curve together with several level curves of the function. Okay, that's what it shows here in figure 1. All right, so you have those level curves of the function, those red level curves, and then you have the constraint function g of x, y equals k. All right, okay, so to maximize the function subject to that constraint, g of x, y equals k, is to find the largest value of c such that the level curve intersects the constraint equation g of x, y equals k. So think of it like this. Think of it like this. Hold on, did the book get lost here? Hold on. let me happens occasionally. Okay, so let me ask you, in figure 1, what is the surface doing as what is the surface doing in figure 1 as you like move in the north east direction? Is the surface increasing or is it decreasing based on the level curves as you move in the northeast direction, like at a 45-degree angle, or just northeast? It could be. Okay, why you're all right, Eric, Robin, and Ryan. The surface is increasing, but why is it increasing? What is I mean, how do you know the surface is increasing as you move out from the origin? You're right. How do you know? How do you know the surface isn't decreasing? Okay, Eric says the value of the function is growing in that direction. That's right. The level curves go, f of xy equals 7, f of xy equals 8, f of xy equals 9. The surface is rising as you move further away from the origin. So, but now the constraint equation is drawn along with those level curves, and you see at the blue point there, the blue point is the actual the coordinate xy for that blue point in the picture is I want to say this the right way. Hold on, let me just say it the right way. Do you see that level curves, that blue constraint equation? Do you see that that the largest value of the function is going to equal 10? If we want to know the largest value of the function such that the constraint is satisfied, do you see it has to equal 10 based on the picture? Okay, that's what I'm looking for. Good. Thank you. So the largest value of the function such that the constraint is satisfied is equal to 10. Is anybody uncomfortable with that? You have to let me know. Okay, all right. So the point xy, okay, the point xy is the point that will maximize the function, but yet satisfy the constraint. And if you notice where that blue point is, what can you tell me about? I mean, if you were to, I want to say this the right way. If you were to draw the gradient of the function and the gradient of that level curve, I'm sorry, if you were to draw the gradient of the level at the level curve, f of xy equals 10, okay, that gradient is perpendicular, right? So what I'm trying to say, maybe I can say it. Let me get the whiteboard up here. Hold on. Okay, so hold on. I'll kind of, I won't recreate the entire picture, but I can recreate part of it. So, okay, so this is the f of xy equals 10. Okay, and so this is based off of figure 1 from section 11.8. hold on. Okay. There's the blue dot. This is G of xy equals k. That's our constraint. And, okay, I'm going to draw on the little picture here. I'm going to draw, hold on here. A vector. What is that vector? What would that vector be? And maybe just to kind of help things, hold on. Okay, that's right, Ryan. That's the gradient vector. So the gradient vector, good. This here is the gradient. No, let's get it in black. This is the gradient. Of the function. And we know this is a right angle here. Okay, let's draw that a little bit. Okay, so far so good. The gradient vector is perpendicular to the level curve at that blue point there. Okay, now I'm going to draw another function too, or another vector also. And actually, hold on, maybe I'll do something else too. One moment. Let's call this point. No. Let's call this point x sub 0, y sub 0. Okay, then the gradient is the gradient at x sub 0, y sub 0. Okay, now let me draw another vector. Let's just say it goes that way. Perpendicular as well. Okay, what's this purple vector that I drew? What would that be? What vector might that be? I'll give you a hint. Well, Eric, good effort. It couldn't be negative the gradient because I drew the purple vector longer. Okay, Robin. That's so, but Eric, you're thinking there. Robin's right. That could be the gradient vector for G at x naught, at x sub 0, y sub 0. Now, I drew the gradient vector going in the opposite direction, but it could also have gone in the same direction The gradient of G could go in the same direction as the gradient of F. But the point is, we know that that gradient of G is perpendicular to the level curve of F of xy equals 10, just like the gradient of F was. So what can you tell us? What can we say then? What can we say regarding the gradient of F hold on. I'll try to use my, hold on. What can we say about the gradient of F and the gradient of G? There's something I'm looking for to put in there. Okay, Eric says 1 is the factor of other scalar multiples. You're right. You're right. So they are parallel to each other. And that means that the gradient of F equals some scalar lambda times the gradient of G. Right? The gradient of F is parallel to the gradient of G, so those one vector is a scalar multiple of the other vector. This value lambda is called your Lagrange multiplier. So this is what I wanted to mention, and this is, you're seeing it for a case where you have a function of 2 variables, but it also works for when you have a function of 3 variables. So if we go back to the, well, first, are there any questions on that? All right. Well, if we go back now to the book, then okay, they, you know, mention the same equation. Okay, it's just they have it for functions of 3 variables, but it's the same principle. And based off of this vector equation, we're going to be able to find maxima and minima of functions relative to constraints. We're using what's called the method of Lagrange multipliers. Okay, so the method of Lagrange multipliers, okay, says to find the maximum and minimum values of a function subject to a constraint, you find all the values of x, y, and z that satisfy the that Lagrangian vector equation and the constraint. And then you evaluate the points to see, evaluate the function to see which of the values is maximum and which is a minimum. So you can have, for instance, like in economics, you might be trying to maximize or minimize some cost function of multiple variables relative to a constraint on maybe, you know, how much of each product you can use. I mean, this is a very big topic, and you know, we're going to be looking at it here in multivariable calculus sense. But tell you what, they talk, for instance, in example 1 in the book they have an example where you maximize the volume of a function using Lagrange multipliers. Okay, but what I want to do here, is I'd like to look at example 2. Example 1's a great example, but I have I have some examples I want to look at with you. But example 1, maximizing a volume using Lagrange multipliers. I'll let you look at that. It's a wonderful example, but just because in the interest of time, I kind of want to start off with a simple, a little more simple example. Okay, so example 2 in the book here says find extreme values of the function on the circle x squared plus y squared equals 1. So for this problem, blow that up a little bit, your constraint is that the points have to be on that circle, x squared plus y squared equals 1. But the function you're maximizing, or, well, you're looking for extreme values, that could be maxima or minima, of this paraboloid. That's a paraboloid. F of xy equals x squared plus 2y squared is a paraboloid. You want to maximize or minimize that function. You want to find the extreme values, but you're requiring that the points satisfy the circle. So what you have to do is you have to, of course, hold on here. They write it their own way, but do you see that if you're going to satisfy this vector equation, then if two vectors are equal to each other, then the components of the vectors have to be equal to each other. So what they do then is say, okay, well, if that's the case, then these two equations, partial of f with respect to x equals lambda times the partial of g with respect to x, and the partial of f with respect to y equals lambda times g, partial of g with respect to y. Those have to be satisfied. And you still need the constraint to be equal to 1. So based off of that, you come up with two equations. You come up with two equations here. Okay. Come up with these two equations. And based off that, you can solve. So I'll tell you what. I think what I'm going to do. Well, no. Let's finish this. Let's just finish this one. All right. So sorry. I don't know what's going on here. I want to get to the. Yeah, here it is. Yeah. So you have these equations, and based off of the equations, I want to say this the right way. Based off the, like from equation 9, I'm going to have to, hold on class, let me go back to sharing it. Blowing it up is a little bit too restrictive. Okay, so yeah, based off equation 9 there, okay, you have 2x equals 2x times lambda. Now, when would that be true? 2x equals 2x times lambda, equation 9. When would that be true? Okay, well, if we go to the whiteboard, we can write that down. Okay, and we can. So I kind of want to do an easier example with you. This one. Okay, so Christopher, and you have your ebooks also. 2x equals 2x times lambda. So that means then 2x minus 2x times lambda equals 0. And if we factor 2x out, we'll get 2x times 1 minus lambda equals 0. So this means you have two possibilities. X could equal 0, or lambda could equal 1, or your Lagrange multiplier could equal 1. So this is something new. You've never probably seen something like this before. But basically, we're just working with these these set of equations to try to get where the maxima and minima are. So x equals 0 or lambda equals 1. But are there any questions on this? And you notice I don't divide by the variable. In this case, I'm not going to divide by the variable. If I divide by the variable x, I have to justify that I can do that. And we can't justify that here. So if we go back to the problem then at hand, okay, if we go back to the problem at hand, if x equals 0 or lambda equals 1, x equals 0, then if we put x equals 0 in the constraint equation here, you're going to get y equals plus or minus 1. On the other hand, if you put lambda equals 1 in this equation here, okay, you're going to get y has to equal 0, because if lambda equals 1 in this equation 9 here, then 4y would equal 2y, and the only solution from that is y equals 0. So if y equals 0, then you feed it in the constraint equation, you'll get x equals plus or minus 1. And so this gives you then four possible extreme values for this particular function. In other words, if we look at like a picture, if we look at a little picture here, okay, here's the surface z f of xy equals x squared plus y squared. Okay, this is example 2 we're looking at, and they draw a circle, x squared plus y squared equals 1. So do you see at the points 1, 0, 0, 1, negative 1, 0, and 0, negative 1, those are points where the surface, those are coordinates where the surface would be either maximized or minimized for that particular constraint. I think the picture really helps a lot. I really do. Do you see that okay? Yeah, and where are, okay, thank you, Ryan. And you can see that well, for what coordinates go with the maximum? They give you 4 coordinates in this problem. They give you 4 coordinates. Okay. F is 0, 1, F is 0, negative 1. Well, 0, 1, 0, negative 1, 1, 0, negative 1, 0. And they evaluate the function at those values. And you see that at the coordinates 0, 1 and 0, negative 1, the surface is maximized, subject to the constraint. And at the points 1, 0 and negative 1, 0, the surface is minimized, you know, subject to that constraint that the x squared plus y squared equals 1. Is this all right? Are you kind of... All right, so Robin has a reasonably good feel. And I think we need to do an example, or two to help you with this. So let's go to the to our notes. We're going to do a few examples. But are there any questions on this? How many think a few other examples will help? More examples will help. Okay, Diodath agrees. Okay, great. Eric and John agree. Great. Okay. Well, then let's get to that. All right. So okay. Let me give you a moment to copy this example down. Okay, and I sent a message to one of you, private message. If you can respond, I'd appreciate it. Oh, I guess there must be a chat thing or something, Jamal. Okay, and the student replied. Excellent, thank you. Okay. And I just sent another student a quick, just a little private message. You know, so check your email, check your little chat thing there. And okay, good. Okay, all right. So, well, all right, let's see what's going on here with this problem. We want to find the minimum distance from a point 1, 0, -2 to a plane using the method of Lagrange multipliers. Okay, may I move forward with the solution? All right, very good. All right, I always like to make sure I'm pacing myself. Okay, so in the solution, what I do is I draw a picture of a plane, okay? I draw the point 1, 0, -2, and I draw a plane, and in this case, my plane is, what is my plane? It's x plus 2y plus c equals 4. So x plus 2y. Okay, John's back with us. Excellent, John. X plus 2y plus z equals 4. And, you know, I drew the plane at kind of an angle because I know this is an oblique plane, because I know the vector 1, 2, 1 is perpendicular to the plane. So I just drew a, you know, a plane. And so there's a point 1, 0, negative 2. Now is 1, 0, negative 2, is that on the plane? Is 1, 0, negative 2 on this plane? No, it doesn't satisfy the equation of the plane, and you know, we don't want it to, right? So we have a point that's not on the plane, but since the point lives in three-dimensional space and the plane lives in three-dimensional space, there's some minimum distance between the point and the plane. And in this case, there's only one point that will satisfy the minimal distance. It's like that movie. What's that movie with where the guy gets stranded on Mars? What's that guy's name? He's a famous actor. The Martian. The Martian. Is that the name of the movie where they got to go rescue him? Matt Damon. That's right, Eric. Yeah, and you know they got to figure out when the spacecraft is going to be closest to the planet, right? So minimum distance, right? Same kind of thing here, you know. All right, so first of all, we have to identify what function we wish to maximize. Okay, well, in this case, minimize, because we're looking for the minimum distance. And there would be no such thing as a maximum distance in this problem. So the previous problem, example 2 in the book, we were using the Lagrange method of Lagrange multipliers. We identified maximum and minimum values, or points that would give us maximum and minima values of the function. But in this case, the distance, we can't have like a maximum distance. We can only have a minimum distance. Because if you give me if you think this is the maximum distance, I'll find you another maximum distance, you know? So there is no maximum distance. All right, so the distance function between the 2 points, right, Eric, infinity, that's right. Excellent. The distance between the 2 points 1, 0, negative 2 and x, y, z is given here. Okay, and you know that how to find the distance between 2 points. You learned that back, I think maybe the first day class in section 9.1. So that's the formula to get the distance, and so this is the distance. But the problem is, this distance here is difficult to maximize or minimize because of the square root. So what we do is we do a little trick here. We say to ourselves, minimizing the distance d is equivalent to minimizing the square of the distance. I mean, if you find the square of the distance, if you minimize that, then you're minimizing the distance, because it's a one-to-one correspondence between the distance and the distance squared. So I'm going to define my function that I want to minimize as d squared. That's going to be my f of x, y, z. Okay, and so that's my function. And I want to minimize the function subject to the constraint that x plus 2y plus z equals 4. That's so that this coordinate that I'm looking for, this x, y, z coordinate, is on the plane. You know, I'm interested in the point on the plane that's closest to the point 1, 0, and negative 2. So when you do these problems, you always have to set up you have to identify the function that you're trying to maximize or minimize, and you have to identify your constraint. Okay. Are there any questions? Who's feeling good so far? Eric's good? Okay. May we move to the next page? All right. Okay. Very good. Wonderful, wonderful. Okay, so now hold on here. Hold on. Where, yeah, I just had it. Okay, it's right here. So now what we have to do, is we have to set up our, well, we have to compute the gradients of f and g. So that's what I do. Here's the function f, I compute its gradient. Here's the function g, I compute its gradient. And hold on here. One moment. Yeah, by the method of Lagrange multipliers, okay, we wish to find x, y, z, that point, such that the gradient of f equals lambda times the gradient of g, subject to my constraint. So what I do is, if I'm looking then for this to be true, the gradient of f equals lambda times the gradient of g, then that means, for instance, that the x component of the gradient of f is going to equal lambda times the x component of the gradient of 1. All right. Similarly, the y component of the gradient of f is going to equal lambda times the y component of the gradient of g. So 2y would equal lambda times 2. Okay, finally, the z component of the gradient of f is going to equal lambda times the z component of the gradient of g. And so you get these three equations. And I number my equations. I put numbers on the equations so I can follow my work in case I make a mistake or something. These are sometimes called the Lagrangian equations here. Okay. And how many like variables unknowns are in these Lagrangian equations? Okay, that's right, Eric. X, Y, Z, lambda. So you have four basically unknowns here. You have four unknowns. How many equations do we need when we have, if we have four unknowns? Well, if we have four unknowns, we're going to need four equations. Oh, okay. Well, where's the fourth equation? What's the fourth equation? I have my three Lagrangian equations here. Where am I going to get my fourth equation from? So I've used this up. I've done gradient of f equals lambda times gradient of g, and I've gotten three equations from there. But where am I going to get the fourth equation? That's right, Ryan, the constraint. And you notice I call that equation 4. So these 4 equations are going to be enough to help me identify the coordinate that minimizes the distance. So kind of when students see this, they think, man, this is a little crazy what's going on here. But it isn't. It isn't. You're just utilizing you're comfortable with this vector equation, gradient of f equals lambda times the gradient of g. So everything else that follows, should be okay. So what I do is these equations here, okay, my Lagrangian equations, I re-express them as these equations. So for instance, the first equation 1, right, is 2 times x minus 2 equals lambda, right? And so I can solve that. I can solve that for x. 2x would equal lambda plus 2, and so x would equal lambda plus 2 over 2. And that's what I got here. Second equation, y equals lambda, that's sort of obvious. And then the third equation, you'll based off of this, well, yeah, that's right, Eric. Based off of this equation here, you can get this equation. And that's exactly right. We're going to take these 3 equations, and what are we going to do with them? We're going to plug them in equation 4 and see what happens. So you have to use all 4 equations. And we haven't used equation 4 yet, so we have to plug the equations. We have to substitute equations 5, 6, and 7 in equation 4. All right, are there any questions so far? Okay, well let me move forward then. May I move forward? Is anybody? Maybe a few thumbs up if you're. Let me know if you need more time. If you don't, I'll move forward. Okay, very good. All right, well then here we go. We're going to substitute equations 5, 6, and 7 into the constraint equation. This was equation 4 right here. And so they get substituted in for x, y, and z. And now we can solve for lambda. We can solve for lambda. Excellent, excellent. Okay. All right. I'm getting better at this chatting, these little chat things. So, okay, lambda equals 5/3. And now what we're going to do is we're going to put that lambda value back in equations 5, 6, and 7 so we can get x, y, and z. All right, and so absolutely fascinating. So now we know the coordinate. The coordinate is 11, 6, 5/3, and negative 7, 6. Okay, that's the coordinate, and you know WebAssign wants exact answers, and unless you're told to approximate. All right, so now what we need to do is we need to get the distance. So we have to substitute in our values of x, y, and z in the distance equation. So if there are no questions, I'll move forward to the next page. Okay, so therefore this point is the point on the plane closest to the point 1, 0, negative 2. And oh, what's the distance? Okay, I computed the distance here. And WebAssign is going to want a simplified answer in simplified radical form. So I did that here for you. I want to mention the assignments for sections 11.7 and 11.8. The reason I have, of course, they're not going to be, well, 11.7 you'll have until what is it, Sunday, the 21st to do that one, and then the section 11.7 will be due Sunday the 21st, and section 11.8 assignment will be due on Tuesday the 23rd. Okay, so 11.7 will be due Sunday the 21st, that section, and section 11.8 on the 23rd, it'll be due. And I have passwords on them because I need to make some, I'm not quite done editing those, so that's why. But I will, soon get the passwords off of those. I don't think anybody's done completely with 11.6 yet, so although I could be wrong, but I don't think so. Okay, so that's the answer. What I did here was I wrote 150 is 25 times 6, so that the square root of 150 is the square root of 25 times 6, and so it comes out 5√6. How many think this is a pretty cool application? Yeah, John likes it. And Eric and Marvelous. Good, good. I'm happy to hear that. Happy to hear that. Okay. Well, let's look at another example that, well, no. Who needs a little more time to copy? Okay, then let's go to the next example. Okay, let's look at this one. So normally I would have you work a little bit, but I just think we need to do this one, 11.8. I just think we need to do it. So let me give you a moment to copy it. Okay, so here, now this problem is a little bit trickier because a little more difficult because we want to find the minimum distance from a point to on the surface, on this surface, which is not a plane, to the origin. So this surface here is a nonlinear surface. Okay, so is it possible there could be multiple points that might have a minimum distance? Multiple points on the surface that's right, Ryan. There, because sometimes these surfaces kind of double back on each other, and they just act, very interesting. So, but the procedure's the same. And keep in mind, the origin has the coordinate 0, 0, and 0. Okay, so that being said, we proceed just like the first problem. So what I do is I draw a little picture, just kind of in my mind, of a nonlinear surface. The origin is, of course, not on this. It's not on this nonlinear surface. The nonlinear surface, incidentally, is, I mean, you wrote it down, but it is x times y. Let me use my, hold on. Got to get used to this stylus a little more here. I'm getting more used to it. I'm getting more used to it. X times y plus 2xz equals 5 root 5. X times y plus 2xz equals 5 root 5. Okay, so, all right, we wish to minimize the distance between the surface and the origin. And in my little diagram here, I just sort of note to myself that, hey, it's possible there could be two points that are minimum distance. There could even be 3 points or 4 points. Who knows? You know. But all right, so we're going to minimize the square of the distance, and that's going to equal x squared plus y squared plus z squared, subject to this constraint. So I compute the gradient vectors for both f and g. Okay, giving you a chance to copy here. Okay, so may I go to the next page? Think we're good here? All right, so then if the gradient of f is when it equals lambda times the gradient of g, that's going to yield these Lagrangian equations, equations 1, 2, and 3. Now this is going to be a little more complex to solve compared to the first one, to the first example we did, because we are dealing with a nonlinear surface. Okay, so it's going to be a little more complex. And incidentally, the book has we're dealing with maximizing, minimizing a function subject to one constraint, but you can extend this to 2 constraints, and the book talks about that. We won't have time to go over that, but there's a nice example. We won't have time to go over that today, but there's a nice example in the book. Example 5. But at any rate, let's stick to what we're doing here. So by equation 2, x is going to equal 2y over lambda. Now, by the way, the equation 4 is going to be my constraint equation. Okay, I call that my constraint equation, equation 4. So x equals 2y over lambda, I'm calling that my equation 5. Again, I like to number the equations so I don't get lost. But look what I did here. Now, I divided by lambda. Okay, whenever I divide by a variable or lambda, I really need to be sure lambda can't equal 0. Well, it turns out lambda cannot equal 0. The reason is if lambda equals 0, then equations 1, 2, and 3, by those equations, it would imply that x, y, and z equals 0. I mean, like for instance, the second equation, if 2y were equal to 0 times x, well, that means that 2y equals 0, and y would have to equal 0. Okay, that's just, I'm just trying to justify, that there. But, that can't happen because well, for one thing, you're at a point on the origin, it's not on the surface, right? And the origin's not on the surface. 0, 0, 0 is not on the surface. It would be silly, right? We're trying to find points on the surface that are a minimum distance from the origin. So of course, 0, 0, 0 is not on the surface. So dividing by lambda, it seemed a little strange to do that. We're taught not to divide by variables, but we can divide by variables so long as they're not. I got to be a little careful here. So long as you don't lose the root of an equation. So the variable can't equal 0, right? Okay, so all right, then what I'm going to do is this equation 5, I'm going to substitute it in equation 3. So remember, I have to make use of all 4 equations. I have to make use of all 4 equations. And I've made use of equation 2, which, because that was the easiest, I've made use of equation 2. Now I have to make use of the other equations. All right, well, I'm going to substitute this equation 5 in equation 3. And if I do that, I'm going to get 2z equals lambda times 2 times, 2z equals lambda times 2 times 2y over lambda. And the lambdas will simplify out. And so you'll get 2z equals 4y, so z equals 2y. Okay, I'll call that equation 6. Z equals 2y. Okay, and now I've utilized equations 2 and equations 3. Those are the easiest. So I know I have an expression for x. I have an expression for z. Okay, so z equals 2y. Okay, and x equals equation 5. X equals 2y over lambda. So what x equals 2y over lambda. Okay, that's equation 5. So what do you think I'm going to do with those equations? That's right, Eric. Put them in the first equation. That's right. Put them in the first equation. And that's what we'll do. So if I may move to the next page, I'll show you that. Are there any questions? All right. The first equation was, the first Lagrangian equation was 2x equals lambda. 2x equals lambda times y plus 2z, right? So, okay, I substitute in 5 and 6. Again, I'm always numbering my equations, so, it helps me not get lost. And I'm going to end up getting here 4y over lambda equals lambda times 5y, okay, which means then that 4 over lambda would have to equal 5 times lambda. Okay, and by the way, okay, I divided by I want to be careful here. Actually, this here where I say y can't equal 0, this actually is not, I don't need to worry about this. I don't need to worry about that because I didn't divide by y at all. So you can ignore this comment. You can ignore that comment. That comment, when I say 4 lambda, 4 over lambda equals 5 times lambda, I didn't divide by y here. So this is not relevant, that comment. That's good. That's less for you to copy, right? So 4 over lambda equals 5 times lambda. That means then that we'll multiply this equation through by lambda. 4 equals 5 lambda squared. Lambda then, hold on. This should be lambda squared here, right? So lambda equals plus or minus 2 over root 5. Okay, so here we actually got a value for lambda. Okay, so we're going to make use of this, but we're indeed going to make use of this. We're indeed going to make use of this. But what's the only equation we've not used so far in this problem? What's the only equation that we have not used? That's right, Ryan, the constraint, equation 4. So I'll go ahead and substitute in, hold on here, equations 5 and 6 in the constraint. And if I do that, here's the constraint. Equation 5 said that x is equal to 2y over lambda. And equation 6 said that, I guess, yeah, we have x twice here. And then equation 6 was that z was equal to 2y. So I substitute that in. And I'm going to end up getting y squared equals 5 root 5 over 10 times lambda. Okay. So this, I always think of this, I don't know if this is a good analogy, but I used to watch wrestling. When I was a kid, I would watch wrestling, you know, on TV. What's it called? The WWF or WWE, World Wrestling Federation. How many have heard of that? Worldwide Wrestling. How many maybe watched that a little bit? I don't know. John does, Robin does, and so so you know the men and the women, they're women in now too. You know that they do what they need to do to solve the to win the match. You know, whether they, you know, sometimes they gotta, you know, get a chair and hit somebody with it. You know how it is. Okay, they sometimes they'll have a buddy come and help them. You know, it's crazy. You know. So that's kind of how I look at the analogy. I think of these problems. I'm doing what I need to do to try to solve the problem. And right now I got y squared equals 5 root 5 over 10 times lambda. But I'm happy with that because, you know, I got to either solve for x, y, or z. I got to solve for one of these variables. Well, look, lambda, we know that lambda is equal to plus or minus 2 over root 5. So I'm going to say, well, let's go with lambda equals plus 2 root 5 first. If I substitute that in for lambda, I'm going to get y squared equals 1. And so y will equal plus or minus 1. And so now the problem falls apart. I mean, it unwraps like a flower or something, blossoming flower. When y equals 1, I solve x. I can solve for x and get root 5. And I can solve for z because z is equal to 2 times y. And when y equals -1, I can't ignore -1, right? When y equals -1, I can solve for x. X equals negative root 5. Z equals -2. And I get the point. And so I got 2 coordinates here. I have 2 coordinates on the surface. You can check that they're on the surface, substitute them in the surface equation, and you'll see it satisfies that. I got 2 points that are closest to the origin. So if this is the space, if this is like, I got to be, well, 2 places that Matt Damon can jettison off of Mars and have the shortest distance, right? If he's trying to land on that surface, I don't know, in space or something. All right, let you copy here. All right, so is there anything left to do? We have two points here. Are we like completely done with the problem? Well, Ryan's right. We have to find the distance, but what else maybe do we need to consider before could there be other points that on the surface that are of minimum distance to the origin? I mean, okay, good. Robin's saying you have to consider lambda equals -2 over root 5. Okay, we got to consider that. So on the next page, I will do that. May I move to the next page? All right, thank you, John. All right, so everybody sees here I'm dividing by 2 root 5 right here. It got cut off a little bit, but you see it there. Okay, so what about when lambda equals -2 over root 5? All right, the y squared equals 5 root 5 over 10 times lambda. I put the -2 over root 5 in for lambda, and I get y squared equals -1. But if I solve that, I'm going to get y equals plus or minus I. Oh, do we want imaginary solutions here, class? Do we want imaginary solutions? Are we interested in that? No. Our surface and our coordinate are in 3-dimensional real space. So, we're not dealing with complex space. We'll save that for another class, okay? So, therefore, it's official. Root 5, 1, 2, and negative root 5, -1, -2 are the points on our surface closest to the origin with distance square root of 10. Okay, it's official. Now, how do I get the square root of 10? Well, the distance squared was equal to x squared. Hold on, maybe I can. Yeah. Hold on. distance squared was x squared plus y squared plus z squared. Well, whether you have this coordinate or this coordinate, if you substitute it in here, you're going to get 10. You're going to get 5 plus 1 plus 4. And square root then of 10 is square root of 10. So I wanted to do, a little bit harder problem with you. The example 1 in the book is a problem where they maximize a volume using Lagrange multipliers. They have a rectangular box without a lid is to be made with 12 squared centimeters of cardboard. So that's a good problem to look at also. And I think after you're seeing this problem, I think you'll be okay to look at that problem. Okay, are there any questions? Okay, let me stop the recording.